Hello and welcome back. So over the next 3 videos we're going to look at sequences. In this video it will be very simple sequences. After that, linear sequences, finding the nth term, and then finally looking at quadratic sequences. Okay, this video, simple sequences. So what we're looking for here are patterns between each term. Well, what's a term? This is the first term, this is the second term, third term, and fourth term. Between the terms, we look at what's going on. So you could say we are multiplying by 2 or we're adding 1. Again, we could say we are multiplying by 2 or we are adding 2. In this case, you could say we're multiplying by 2 or we're adding 4. And what you're looking for is a common rule. A rule that is the same between each term. So obviously add 1, add 2, add 4 is not the same. But multiplying by 2, multiplying by 2, multiplying by 2 is the same. So we can see in this set of sequences something called the term-to-term rule is multiplying by 2. So our next sequence will be 8 multiplied by 2. Our next one will be 16. Doing the same for question 2. So there's no simple multiplier here to get to 10. So it looks like it's adding 3. Well, that seems to be adding 3 as well. And that seems to be adding 3. So if we add 3 to 16, we get 19. So that's our next term. In this case, our term-to-term rule is to add 3. If we look at this one here, there doesn't seem to be an obvious rule here. Now we look at this one, we are adding 0. This one, we are adding 1, adding another one, adding 2, adding 3, adding 4. Now this is a bit more challenging. It doesn't look like there's a straightforward sequence here. Is the next one add 5? I don't know. We need to look at this a little bit differently. So this sequence is quite a special sequence. If you look carefully, 2 is made up of 1 plus 1. 3 is made up of the 2 plus 1. 5 is made up of the 3 plus 2. So in this case, we're actually adding the previous 2 terms. So we haven't got a term here, we'll call it 0 for argument's sake. That one there is the other term added, so it's just 1. This one is 1 plus 1, which is 2. This one here is 2 plus 1, which is 3. This one, 3 plus 2, which is 5. This one, 5 plus 3, which is 8. And this one, 8 plus 5, which is 13. So our next term will be the 13 plus the 8, which is 21. So this one is you're adding the previous 2 terms. This sequence has a special name. It's called the Fibonacci sequence. It's worth searching that. Have a look at where we see the Fibonacci sequence in nature. So number 4, hopefully you can see this is fairly easy to spot. The numerator stays the same. We are multiplying the denominators by 10. So if we take the last one and multiply that by 10, our next term would be 1 over 20,000. So in this case, we multiply denominator by 10. Now, one thing I didn't say here is you want to actually describe this rule properly. The top one, for example, you would say we start at 1 and the term-to-term rule is multiplying by 2. This one, you'd say start at 7, then the term-to-term rule is add 3. This one, start at 1, add the previous 2 terms. And this one, start at a half and multiply the denominators by 10. Let's move that forward. So in this case, rather than find the basic term, we're going to write down the first 5 terms for each sequence. So we're introducing here something called the nth term. Well, the nth term means the value in the sequence at the position n. Well, position n is any position you decide. So if I want the first 5 terms, n is equal to 1, then 2, then 3, then 4, then 5. So I've written here position 1, 2, 3, 4, 5, and that can continue on forever, going to whichever position I choose. So for term 1, the value in the sequence will be 2 multiplied by the position in the term. All I'm doing is substituting the position into the expression. So I have 2 multiplied by 1, which is 2. Then I take this 2 here, the position 2, multiplied by 2, which is 4. We're saying these position values are n. 2 multiplied by 3 is 6. 2 multiplied by 4 is 8. And 2 multiplied by 5 is 10. So that's the first 5 terms. We can do the same thing here. 3 times 1 is 3, add 2 is 5. 3 times 2 is 6, add 2 is 8. 3 3s are 9, add 2 is 11. 3 4s are 12, add 2 is 14. And 3 5s are 15, add 2 is 17. They're the first 5 terms in our sequence. All we're doing every time is replacing n with the position number 1, 2, 3, 4, 5 because we've been asked to find the first 5 terms. Nothing changes, we do the same thing, we put 1, 2, 3, 4, 5 in here. So 1 squared is 1, minus 1 is 0, 2 squared is 4, minus 1 is 3. 3 squared is 9, minus 1 is 8. 4 squared is 16, minus 1 is 15. And finally, 5 squared is 25, minus 1 is 24. This one looks more complicated, but the principle is the same. It is pure substitution. So we are going to find a half of whatever n is, and we're going to multiply it by n minus 1. So in this case, a half of 1 is 0.5. 1 minus 1 is 0, and anything times 0 is 0. A half times 2 is 1. 2 minus 1 is 1, and 1 times 1 is 1. A half of 3 is 1.5. 3 minus 1 is 2, and 1.5 times 2 is 3. A half of 4 is 2. 4 minus 1 is 3, and 2 3s are 6. Finally, a half of 5 is 2.5. 5 minus 1 is 4, and 2.5 times 4 is 10. So that's a very quick introduction to simple sequences. If this is of use to you, please like and subscribe. Now hop on to the next video and have a look at how to find the nth term for linear sequences.